All right, guys, so we are looking at solving inequalities. Basically, there's one big rule for solving inequalities that makes it different from an equation, and because it's got that little symbol going on. And we basically need to know there are some times when it's going to turn around and other times when it stays the way it's at. The rule for what we're mostly going to look at is if you divide by a negative at that last step, you will flip whatever the inequality sign is around. Just to briefly show you where that comes from so it's not just totally random, what I did is I started with something that's true, like 24 is bigger than negative 12, so we agree with that. I wanted to just look at steps that we do to equations, right? We do stuff to both sides. We add, we subtract, we multiply, we divide, sometimes with negatives, and we just want to make sure that all of those things maintain it being true, then we're allowed to do it. And if it doesn't, then that's something we're going to adjust. So just real quick, when I add 3 to both of these sides, I get negative 9 is less than 27. And I still agree with that statement. Timesing by 2, I agree. Dividing by 6, I agree. When I start subtracting, okay, I owe $4 more. I owe 16 is less than 20. Owing $16, that's still true. And up to this point, you're kind of like, all right, it seems like we could do everything we've ever done. When I multiply by 2, I get 24 is less than a negative 48. I'm like, wait a minute, owing $48 is not better than having $24. That's false. And similarly, if I divide by negative 4 here, I get positive 3 is less than negative 6. And that again is something that I disagree with. So what I said in our rule was is if you divide by a negative, and technically also if you multiply, but if you think about our problems, usually that last step is a division step, and that's why I focus on the rule being that. If you divide by a negative, then you need to flip this sign around, because if I flip it around, then you're saying having $3 is better than owing $6 negative, right? I would say that's now true. So as long as we turn it around, if that happens, then we're allowed to do that step. So let's see a couple of examples. I'm going to work them a little bit quicker just because we've been working on equations now for a while, but it should still get you the steps, and I want to point out what's new. So when I distribute here, I'm getting 8x plus 2 is less than negative 14. At this point, I'm going to move the 2 to the other side and get minus 2. Okay, it's kind of a quick way of writing minus 2, minus 2. So get 8x is less than negative 16. Divide both sides by 8, and I get negative 2. And according to my rule, I just checked. That last step that I just wrote, I did not divide by a negative number. I divided by positive 8. So I don't change this around. And I picked this example just to point out it doesn't matter if your answer is negative. It doesn't matter if that 16 was negative. The step you wrote was a division by positive, so it didn't change. Cool. I'll go back and talk about the graphs when we're done with all 4. Here we've got x's on both sides. These 6x come over. They're now negative. Again, using that same kind of slide it over and change. If you want to write minus 6, no problem. Okay, but that's how I like to do these. 3, negative 3x, negative 6. This 3 moves over, becomes a negative 3. Negative 9. Divide both sides by negative 3. I get x, I get positive 3. And this is an example, put a big star by it, that I divided by a negative, this sign then turns around. Over here, both of the x's are on the right. That's fine, I'm probably just going to leave them there. They go ahead and combine to 10x. Okay, because we didn't have to move it to the other side. They're on the same side, that's why they're not changing. Okay, this, however, does need to go over there. Changes to plus 5. I get 50 less than 10x. Divide both sides by 10, gives me 5. I did not divide by a negative, this sign stays the same. This example is on here to address the case of, well, I want my x on the left. Like, this is how I label my answers. So if I do need to spin this around in order to label my answer, make sure, if you think like elementary, like if it's chomping at the x right now, it should still be chomping at the x. If I have to physically take this problem off the board and spin it around, then the inequality sign has changed with it. Lastly, I wanted you to see an example of a special case. So I'm going to combine the 3x plus x, right? They're on the same side, we're not moving them anywhere, so 3 and 1 is 4. Over here I can distribute and get 4x plus 8. X's are on both sides, so when I move it, it does change. And this again is our special case. Anytime the variable completely goes away, it's either infinite solutions or no solution. And what determined that was whether what was left staring at me was true or false. So I have a -5 is less than or equal to a +8. And I basically have to say, do I agree with that or not? I agree that 8 is bigger than -5. And because that is true, and because of that, the answer I'm going to write down is infinite solutions. Okay, so let's briefly talk about these graphs. Basically, you notice the number line doesn't have anything super fancy on it, so as long as the -2 ends up over here, +3, okay, the +5, and infinity we'll talk about because it's a special case. What you were supposed to remember from junior high is that you put some kind of a circle there, and you had to remember whether it was filled in or not. The difference is if there is the equal to under it, it's going to be filled in. So here's the deal. In these problems, we shade where things are correct, because we're not saying, let's use this one, we're not saying that x equals 3. Okay, our math got me to a number 3. What it's saying is every single possible number in the universe that is less than 3 or equal to 3 is a solution. So 2 is less than 3, 1 is less than 3, 0 is less than 3. In fact, everything over here is less than 3. So we shade all of that in. Okay, so just to think about that on here, we're saying all the x's that are less than or worse than owing $2. Well, as I get more negative, again, the less thans are this side of the graph. This says all of the numbers that are bigger than 5, greater than 5. So that's like 6, 7, 8, everything that's over here. So going back to what goes inside the circle, we're basically saying, is that number also part of the solution? So if I say, is 5 bigger than 5? No. So I leave that blank, like to show that I'm not an answer, just everything after me. But here, if I plug in 3, 3 is less than or equal to 3, then yes, so the point itself is like part of the shading. And we zoom in on that point to specifically highlight that to whoever's looking at it. Lastly, infinite solutions means every single thing is a solution. So as silly as this is, you put the arrows, you shade the entire graph because everything is an answer. Now, didn't happen up here, but for example, if I had no solution as example, let's say it was -5 is bigger than 8, and I was like, owing $5 is not better than having $8. That's worse. That is false. That is no solution. Then my graph stays blank. Like, that would be my graph. Everything's an answer. Nothing is an answer. All right. Hopefully that helped. Have a good day.